Great. So we're really happy to have Andras with us, telling us about quantum random walks.
Thank you. So I'm trying to make this talk accessible. So if anything, I go too fast or like I didn't explain some detail, then please don't hesitate to stop me for any questions. And well, I was told that you are still like exploring some fundamentals in quantum. So, and I kind of need a concept of projective measurements. So I thought that I would explain a little bit like how projective measurements work. So I start with that.
Yes, thank you. And I just want to say that most of us are beginners, so that would be fantastic.
Yes. Measurements. Okay, so well, here you have some, in the simplest case, you have an orthogonal projector, pi, and its complement. And really, this measurement, just if you are given psi, it will map it to either project it down so you normalize it. Well, maybe I should write it out. So you will just so so you start with say a pure quantum state psi, and then if you measure the projector pi, then this state will be projected down to that subspace of the Hilbert space. But it's not a quantum state because it's not normalized, so you need to normalize it. You will just take the absolute value square of this projected down part so that things become nicely normalized. And this happens with probability, as you expect, is just this norm square. So the norm of the projection and squared as usual, or in the other case, it goes to the orthogonal complement, the other projector, and again divided by its norm. And again, the complementary probability will be, as you expect, just the norm of the other state, which is identity minus pi times the state and norm square. And since your vectors have like unit norm in the Euclidean distance, these probabilities add up to 1, and this is a well-defined process. And you don't have to have only 2 projectors. You can have more of them. So, for example, the usual computational basis measurement also is a projective measurement. So the projectors could also be just all these operators like so if you have an n-dimensional Hilbert space, then you can just take the computational basis measurement, and that will be also projective measurement. If you measure in this basis, then your state gets projected down to the ith basis subspace, like which is just this one-dimensional subspace which is spanned by the ith basis vector. And while with what probability it happens is the projection to this subspace squared, which is just the absolute value square of the ith coordinate. So this is really a generalization of this basis measurement. And so why do we like this, or what's the advantage? Well, the advantage is that maybe in some cases you you actually don't want to learn everything from the state. In a classical scenario, when you like, the more information you learn, you know more, and it's probably helping you. But in the quantum, it's not necessarily the case. So maybe, yeah, I should describe like an example where you have 2 qubits. Do you know how can I scroll in this Zoom thing? Is there a way to somehow move this?
So I think Andras, if you do screen sharing via this the Zoom board, then it's pretty tricky. If you're using an iPad or another tablet, then it might be better if you could just open the Notes app of your particular tablet device and use that to share your notes, because that way you can scroll. But Zoom's Blackboard or whatever this thing is called is not very good enough. Is not good enough for sort of scrolling down and stuff. I mean, unless people have figured it out, I couldn't figure it out.
Okay.
Sorry, Andras, this is Vinod. Are you using an iPad?
Well, I'm using Windows.
I see. Okay, then I'm out of luck.
Well, okay, I just try to make it work this way. Okay, so people sometimes say that let's measure a Hamiltonian, and what does it mean? So suppose that you have a Hamiltonian, which is in this case, just to be concrete, it could be like Z tensor Z. So it is just 2-qubit Hamiltonian. And well, in this particular case, I can write this as a sum of so it's a Hermitian operator, so I can diagonalize in an orthonormal basis. And so I want to write down an eigen decomposition, but in terms of eigen subspaces. So I don't want to distinguish things which have the same eigenvalue. So I can write this as so the sum of the +1 eigenvalues, which will be sorry, it would be 0, 0, tensor 0, 0, plus 1, 1, tensor 1, 1 times 1. So this will be the first term is the projector to the eigen subspace of eigenvalue +1, and then I need to write down the projector to the eigen subspace of eigenvalue -1, and that looks like this, times -1. Okay, so when you have a Hamiltonian, then you might have like even more eigenvalues, but in this case you have just two eigenvalues, and you can decompose your Hilbert space according to these projectors. And then what we mean by measuring this Hamiltonian is really just construct this eigen subspace decomposition and do a projective measurement according to these projectors. And then if like people start talking about expectation values, that's just take the measurement outcome. And if you measured like this first projector, then say output 1, because that's the corresponding eigenvalue. If you measured in the second projector, then output -1, because that's the eigenvalue there. And so why is this useful? Because sometimes you don't want to destroy the fine inner structure of the state. So imagine a scenario that you are given one of two states, and so you are either given like a Bell state, which is like something like psi1, which would be equal 0, 1 plus 1, 0 divided by square root 2, or you are given another val state, which is again a nice entangled state and can be used for, I don't know, crypto protocols or whatever else. And that would be just 0, 0 plus 1, 1. It's another EPR pair, just a more standard one, and have it by square root 2. All right, sorry, apparently it's messing up the whiteboard. Anyway, so you get the idea. You have two val states, and you get, say, randomly one of those. These states are entangled and are very valuable, but if you measure them in a computational basis, you can of course distinguish between the two, because if you measure a different value in the first 2 bits, then you got the first kind of val state. If you measure the same in the both, then you got the second one. But with this measurement, you destroy the entanglement, and it's not a useful state anymore. But if you just measure this ZZ operator as before, then you can see that psi1 is in this eigen subspace of the -1 eigenvalue. So if you measure this projector, then you can detect that you have the psi1 state, and you don't destroy the entanglement, because it just projects down to that subspace, and it's a vector there, and you can keep it. Or if you measure the other in the +1 eigenvalue, that's what you measure in the Hamiltonian, then you can see that you have psi2 state, and again the entanglement doesn't get destroyed. So for this reason, it's useful to have not a full computational measurement, but just this partial measurement. All right. Okay, so this was about projective measurements, and now I want to turn to actual random walks on graphs.
So I have a quick question.
All right.
Erasing. So it looks like projective measurements then are a strict generalization of basis measurements. And these are also physically possible, or is there some difference between physical feasibility of basis measurements and projective measurements?
Okay, yes, these are definitely physically possible, and these are super important. For example, when you do error correction, then somehow this is exactly what you want to do. So you somehow want to detect that there was some error happening without destroying the quantum data stored in your quantum state. So this is without these measurements, it's not possible to do error correction. You kind of want to measure in a way whether there is an error or not by just doing such kind of measurements which check some parity or some other constraints. And if there is some violation in these measurements, you see that there is some error happening, but you detect the presence of error in a way that doesn't reveal any information about what is the actual encoded state that you have. And that's very important, because if you reveal any information about what is your quantum state that is encoded, then you leak information and you start destroying the state. So in error correction, it's very important that you can do measurements which only detect errors, but don't say anything about what was the actual data encoded in this quantum computer.
That makes sense. So if you were to measure some 1-bit predicate of a state, then you could do that with projective measurements plausibly without destroying anything else.
Yes, yes. And okay, so just a little note. So how are these measurements implemented, or how you should think about this, because it's also actually relevant for my talk. So you think about having a unitary, so somehow what would be a coherent version of this measurement. So coherent, it's a unitary which doesn't destroy any information. So that would be, you have your register and you append an ancilla. And so your unitary will be something of this form. So it projects down on the first register to the projector what you wanted. And so this is your state that you care about. And this is just an ancilla qubit. So the state can be arbitrary dimensional, many qubits, but the ancilla qubit only needs to be 1 qubit. And I just described this unitary operator. This is a nice and reversible operator, and it does this. So this is like a coherent measurement. Why is it? So suppose that you have psi, and you initialize your register to 0, then it will map your state exactly to what you want. Basically, it will be psi 0, and then it will, yeah. So that it projects down this part there. And what happens if you are in the other part of this like projective, this subspace? Well, then it just selects out that part, not that part, it flips the second qubit. So if your ancilla is initialized to 0 and you do this unitary operation, then you can see that basically this measurement can be performed by just doing a computational basis measurement in the ancilla qubit. So if after this operator you measure the ancilla, then if you measure 0, then you know that you measured inside this projector pi, and your state will be normalized, and you get it with the probability that you wanted. And if you measure 1 in this ancilla, then you get the other one. So this is how you actually implement this measurement. You do this unitary in ways that work for you, and then you just measure this ancilla. This is how you should think about this. All right. So this is how you implement the measurement in a quantum computer. And well, in the quantum walks, we will use such operators, and we actually don't want to implement the measurement directly always. It's sometimes in the quantum walk updates, it's useful to just have this coherent version and only use this at the very end to measure the state. But yeah, so I try to now turn to random walks. All right, so we have a graph which has some vertices and edges, and we have some weight function which goes from the edges to some positive, non-negative numbers. And so given such a weighted graph, you can define a random process where you are given a vertex V in V, then you move to vertex U with probability that would be the weight of the edge VU and divided by sum of the weights Vx, sum over x. So basically proportional to the weight of the edge going from V to U as compared to all the edges that go out from V, you make a move. And so these random walks that I talk about are particularly in undirected graphs, because those are the ones that work nicely when you start building quantum versions of those. The undirected walks are somehow, no one knows how to make them work, and probably it's expected that you won't succeed with directed walks. And the reason for that is that somehow directed walks have like an inherent direction, can have an inherent direction. Somehow they can accumulate at some point and like do some weird things, whereas random walks on undirected graphs are in a way reversible. And since you have unitaries and like quantum computers, then everything must be reversible. You can't have this accumulation in some sense. So like the nice quantum versions seem to only work when you have these undirected graphs, and then the walk is in some sense reversible. Okay, so now this is definition of the process, and I will call this probability PVU. So this is like the transition probability from vertex V to vertex U. And so this basically just describes a stochastic process, and this P matrix can be also thought as a Markov chain. And if you have multiple steps, then just like repeat this process that corresponds to taking a higher power of this transition matrix P.
Andres, sorry to interrupt in between.
Yeah, maybe. Sure.
So Vinod just pointed out that if you are a host, or hopefully with co-host, this works. There is an icon to the bottom right of the whiteboard with a plus on it, and that should just give you a fresh page. So maybe if you see that icon, you can try to press it next time you want to change the page.
And it will just make a completely new one.
Yeah, so I guess it'll erase this page.
Okay, so maybe I see now the icon. Okay, thank you. That's very helpful. All right. So there are other versions of. So now I described how this discrete time random walks work, and there are also continuous time quantum walks where you somehow have a continuous smooth transition in time, and those also have quantum versions, but those are not the ones I want to talk about now. So I will just stick to this discrete version now. Okay. So actually, these random walks are very useful in computer science for various algorithms, search, and other things. So I just sketch you a very simple search algorithm based on these random walks. But for that, I need to also introduce the stationary distribution. So the stationary distribution is the distribution which remains the same after applying this Markov chain. So it's kind of the limiting distribution of this random process, and that's denoted by pi, and pi of u is really just the weight of all edges going out from u to some x, and divided by the weight of all like yx. So it's sum over x, and here is sum over xy. So this is just the ratio of the total weight of edges going out from u versus the total weight of all the edges in the graph. Yeah. And maybe I should put a 2 somewhere, because this should sum up to 1. And on the top, yeah, it should be a 2, I guess. Well, wait. Oh no, it's fine. Sorry. I kind of count edges at both ends, so it's fine. Okay. So anyway, this is the station distribution, and then this is just one can prove that it's this proportion to this total weights, and so based on this, I can describe like an easy search algorithm. search algorithm. That's very simple one. Just one, you should somehow sample a vertex U distributed as the stationary distribution. So maybe it's a bit confusing that I used this notation for projectors before. Hope it's not too bad. So you can sample a vertex U, and then the second step, you just...
Sorry, Andres, what are we searching for?
Oh, yeah, okay. So indeed, in the search algorithms, you have some M, which is a subset of the sets V, which are somehow marked. And then you assume that you can somehow recognize these elements once you see them. So you like step with probability, while this transition probability is described, transition to random new vertex, and then check if it is actually marked. So suppose that you were at like vertex X, you transition to vertex Y with this probability, and check whether the Y vertex where you are now is marked. And so this thing you will like repeat this step and do several times. Repeat until you find something. Okay, so this is a very simple classical algorithm, and basically the expected runtime of this algorithm is called the heating time. Which is just denoted as HT. That's the heating time of this marked set M. So it depends on the marked set. And so what is the cost of this algorithm? The cost is the setup cost. You need to set up your initial distribution. Then, well, for every step, which is you do in total about heating time many steps, you need to update the walk and then need to check. So this is like sampling. And this is update. This is moving to a new vertex. And this is check. Okay. So like this is a very simple classical algorithm. And yeah, this finds a marked vertex in this like complexity. And if it's clear, then I'm going to clear this slide and go to the quantum version. Okay, good. So, so the quantum version will have the same things. You need to set up an initial distribution. So that will be, you start from a 0 state and you basically just mimic this sampling these elements. So you will have this state, which is sum over U. And since probabilities are squared, in the quantum case, you want the square root of the probability and U. So this is just the station distribution corresponding to this graph. And then you also need an update, which is given some vertex V and the 0 state in the second register, it will map you to V and then sum over U and the square root of the transition probability P V U, and then U will be in the second register. So this is a quantum analog of the update. Like, see, you can see that if you actually just do one step of this walk, so you are given the vertex V, you apply this update operator, and then you measure the second register, then you will find a vertex U there with probability PVU, which is the transition probability. So with this operator, you can clearly implement the updates of the classical walk, but you have more requirement in a quantum case because you have these amplitudes, and so this is a quantum update. And you have also the check operator, which is this measurement, projective measurement operator, but in a coherent way that I talked about. So given V and...
Can I interrupt you for a second? I think I missed what S was. So S denotes the start node of the graph?
It's like, S is like setup or sampling. So this is just to set up the initial distribution, which is the stationary.
Okay.
Later, I will also describe a version where it doesn't have to be the stationary distribution, but the easiest case is when it's the stationary distribution.
Okay. And what is pi?
So pi is this, yeah, maybe it was a bad choice of notation. So here, pi is really the stationary distribution. So this is the probability distribution, which is this ratio of the weights, which is the stationary distribution of the classical random walk, where it converges over a long time.
Okay.
Andras, can I ask a quick question?
Yeah, sure.
So in the classical case, the amount of memory that you require is just depending on how much you need to store the states, right? Here, it seems to depend on the number of steps this algorithm runs for, because each time you do an update, you'll require an extra ancilla bit.
Yeah, I will, well, this is just one update that I didn't tell you how to, okay, indeed. So if you would just do, if you would do this like classically iterate this walk, then sure, you would just do like have a history, but then you actually don't get the quantum speed up. And to get the quantum speed up, you will iterate this process differently in the quantum case. So these operations are analogous to the random walks, but you use them differently in order to get the quantum speed ups.
Okay, thanks.
Okay, so the third operator is the check operator, which is basically doing the projective measurement for you, whether this V vertex is marked or not marked, but does this in this coherent version. So actually flips ancilla qubit based on this information. And so, okay, so how do you actually use this for quantum updates? Well, since you asked, I just described it you briefly. So somehow the quantum walk operator that will be defined in a way which maybe is a bit confusing at first sight. It will be something like U swap U dagger, basically. So what happens? You basically want to avoid this accumulation of more and more ancillas and like keeping many registers. So you only want, at the end, you will basically only work with 2 registers for this and like reuse them registers. That's why you have this form. And why is this useful form? Well, at this point, let me assume that for simplicity, from now, I will assume that the stationary distribution is uniform. That means that the graph is like, for example, regular. If you have regular graph, then the station distribution is uniform because your graph is like kind of like looks uniform. Okay, and in this case, this quantum walk operator just has the following structure. It will be exactly like the transition matrix P appears in the top left corner, which is just your Markov chain transition matrix. And there are some other things elsewhere, but you don't care about those. So somehow, this is why this operator is nice, because it directly relates to this actual Markov chain matrix. And well, it turns out if you also add your reflection here, then this is how you will, this doesn't affect actually, well, it will in some, so wait, I'm confusing myself a little bit. Okay. So if you add the reflection operator on here, then this is how actually people define the quantum walk on this reflection. Okay, the reflection operator on somehow an ancilla. You reflect on the zero ancilla state, that you start with a zero in this update operator, and you want to reflect on that. Then it doesn't change this form of the matrix, but then this quantum walk operator that I call W will have some very nice form, and if you repeat it, the T power of the quantum walk operator will look like it will actually apply a Chebyshev polynomial to your transition matrix. And again, we don't care about the other stuff. Okay, so one quantum walk step is super intuitive. It just encodes somehow the transition matrix in a unitary matrix in the top left corner. And if you repeat it T times and add these reflections, which are somehow necessary to make it nice, then some crazy polynomial of the Chebyshev polynomial of the transition matrix happens, which is clearly some quantum effect. So, and this is where the speedups come in. And basically, we make it rigorous, and we show that in some way, if you don't do this like T steps of this walk, but do some basically do some analogous operators which are like simple but slightly different, I will just like call it like W tilde T. That is like something almost like doing T steps, T repetitions of this quantum walk step, but not quite. But it's then what you actually do, you can get PT square in this matrix. So this is, so if I explain you that you get some Chebyshev polynomial of the Markov chain matrix, then you say me that, okay, it's like nonsense. I don't understand anything. It doesn't make sense to me. And I totally agree, and people were puzzled with this. But if you just do something slightly different than that, then you can, with T steps of this update operator, you get basically T squared steps of this Markov chain. The T squared power of the Markov chain matrix P that just corresponds to making T squared steps of the classical random walk. So somehow, if you have this quantum access and do these clever operations, then you can do quadratically more steps using only quadratically less quantum operations. And this is where the quantum speedups come in. So if this is like on a high level clear, then I will just state the result here. I don't know, then I can erase this.
Andras, one more quick question.
Pardon?
One quick question. So what does the operator U do on the other vertices? So like you described U on V0, it maps it to V summation stuff. What does it do on, say, VW?
Yeah, it doesn't matter.
Oh, it doesn't matter. Okay.
Arbitrary. So somehow it turns out in all analysis, the only thing that matters is the top left corner of the matrix. And that only depends on this operator, on these things that I defined. The other is just arbitrary unitary extension.
Okay.
Like we don't care.
Okay, thanks.
Okay. And so now the theorem, basically, if you run this algorithm, maybe not with, so initially people just used this quantum operator that I described you and took the Tth power, and that was the quantum walk. And now newer versions do something like almost the same, just some funny phases added, which suddenly make things nicer to work with. Then using these algorithms, you can find a marked element in time, which is the setup and the square root of the heating time times the update plus check. Okay, so while the setup cost remains because you still need to do it once, but then you just use this quantum walk operator, which kind of does quadratically more steps than the classical algorithm could do. So that's why you get the speed up here. And so like this is really first from Szegedy, who just used this like simple walk update operators. So these are just, well, basically Szegedy generalized the walk operator of unbindings for element distinctness, and that's where it comes from. And they first could only show that you can actually detect the presence of marked elements. And then later when we added this tilde, this like slight tuning of these update operators, then we could show essentially this result that it actually finds always a marked vertex. So this is just last year. Okay, and so I mentioned element distinctness, and this was like really the starting point of this, and many like collision detection algorithms and other things are just related to that. And so these are just, so it's like applications are here for Johnson graphs. Okay, well, maybe I should mention here that actually in the previous slide, in this walk operator, I should also, this is just the walk operator in the case when there is like no checking, it's just somehow direct analog of the classical walk. But once you have marked vertices, you also do some checks that incorporate in this update. And then that's why somehow the quantum walk starts to depend on the marked set. And so if you have marked vertices, then you do an extra step here, which is also some application of the check and some reflection around that. But I don't want to like write down the formulas. But yeah, so your walk operator will depend on the check because they will depend on the marked set. And so that's how you get the result. I just didn't describe that. I don't want to make the formulas there, but so that's why the checking operator also appears in this runtime cost. Okay, sorry for that. So the applications often use the Johnson graph. Where you have some universe. So you have some set X. This is like your universe. And vertices are of a fixed size K. So what you do is that your vertices will be subsets of the universe of a fixed size, K, and you will define edges between them, between two subsets, if they only differ by one element. So what I mean by this notation is that two subsets have symmetric difference too. So you remove one element from set 1 and add another one to set 2. This is how you get there. And then the symmetric difference is 2. And then we call this an edge. So this is a graph. And so for element distinctness, what you see that if you just start with really just walk on elements, then the setup cost is really like cheap, just like randomly sample element, that's very cheap. But then the heating time is high. Heating time will be something like number of elements squared, I guess, or something like that. And so even if you get a square root of that, you don't get any quantum speed up. So what you want to do here, what on this unbiases observation was that you want to balance these costs. You want to make the setup more costly so that actually the quantum walk will find a marked element quicker. And that's what you do. And that's how Johnson graph comes in. Instead of just like walking on like single elements, you will walk on large subsets of the graph. So each vertex will contain, if you have n elements, then in unbiased element distinctness, so here you will choose K to be n to the 2/3. And then the setup cost will be basically n to the 2/3 because you need to like get all the elements and query them and see if like what is the function value there. So that's really costly to set up. But once you have that, your Johnson graph becomes more dense. Like in the extreme case when the subsets are basically almost all sets except like maybe apart from constantly many elements, you take the full sets. So like K is like n minus 1 or n minus 2. Then your graph is like almost like a complete graph. And then you can very quickly go, so then the mixing time is super quick and you have very low heating times. But then you need to query everything, so setup cost is high. And it turns out if you balance these costs, like how much you can spend on setup and how quickly you can reach a marked vertex, then for this choice, the classical heating time would be like n to the 4/3, but you can take the square root of that. And this is how you get the quantum algorithm for element distinctness. And really, the nice thing is that here you only need to like analyze this heating time and this setup. So once you have these things, once you have this theorem, it's like really simple to cook up applications. You just need to apply this formula. And so that's how element distinctness works. And so I just want to. And there are many applications for collision, so you can just play around with these parameters, and that's how it works. And well, we understand very well what is the mixing time, so it's like how quickly the heating time, how it looks for a Johnson graph, and maybe I should write down this bound which is used. So the heating time is upper bounded by the following quantity: 1 over delta times 1 over epsilon. And here epsilon is the fraction of marked vertices. And in the case of element distinctness, as you say that a subset is marked if it contains any two elements which map to the same element. So somehow the fraction of marked vertices goes up as you take larger and larger subsets. And this also, this delta is like, so this is basically like the mixing time of the walk. And now this is without considering the marked element. So it's just mixing time of the walk. And this also becomes nicer. So as you take bigger sets, your mixing time improves and your fraction of marked vertices improve, and therefore the hitting time goes down. But you need to pay more for the setup because you need to set up these large subsets. And that's why you need to balance this cost, and it just turned out to be n2/3. And one thing here is that, okay, so why is this quantum walk framework useful in this Johnson graph? Well, the big idea is that once you make a transition between two subsets, you only change one element in this subset. So the update cost is basically you only need to update one element and query one more function value. And also, if you somehow have a nice data structure where you store all these subsets in a nice way, then you can also in very efficiently query whether there is this subset is marked, whether there is a collision inside your subset. And most of the technical details, so this high-level description is very simple for element listingness. Most of the technical details go to the following problem. Your vertices are supposed to be a vertex on a graph, but now you start to add all sorts of data structures to it. Some fancy things are lingering, and that is hard to make it work nicely, because remember that we have like a quantum walk, and we somehow use interference, and everything should be always in the same form. So what is very important, unlike in the classical case, whenever you have a vertex which is now a subset and it somehow stores some data structure together with your elements there, regardless of like what path of the quantum walk got to the current vertex, it should always look the same. So your data structure, which stores your elements in these subsets, should be independent of the like update history. And this is something that is not very important in the classical case. It doesn't care. The classical doesn't care about if the data structure looks a bit different, it doesn't matter. But here it's quantum, and you really need interference. And for that, you need to ensure that if you do this update step where you only replace one element by one new element, the data structure that you get will be always the same regardless like how you get to this new element. And so these are technical details which you can work through it, but these are like the most painful of this analysis. But you as a user usually don't need to worry too much about this because other people just like worked hard on this. But in some cases, it's actually a major obstacle to figure out if this is possible to do these updates efficiently. Okay. So yeah, this is quantum walks in this framework, and maybe I just explain like one more general result. So here, so far, I assume that we start from the station distribution, and also for simplicity, I assume that it's uniform. In the Johnson graph, it's uniform, so everything works nicely, as I told you. But in some cases, maybe you want to, maybe it's too difficult to start from the station distribution, or you don't need to do that, or you have a better hint of where marked elements lie, and then starting the stationary is just a fixed choice. Maybe you have a better choice, and you have a better algorithm for that. And then there is also a version of that. And so now this is like the electric network based walks. And here also we had some, so this was nicely analyzed, and and observed by Bellows in 2013. And so we had some recent improvements. Also, Stephen Piddock had independently achieved similar results. Okay, so now you want basically somehow, sorry, my pen doesn't work very nicely now. You want to start in distribution sigma, which is arbitrary, and then you want to get some speed up. And so speed up compared to what? That's the question. So what is the classic quantity that you can beat? And that will be the commute time. Commute time. Well, and this commute time, actually, in the most general case, it will be like some electrical quantity. So imagine that you have a graph, which, I don't know, looks something, whatever. Then you can have some marked vertices. Say these are this, maybe I can use different color. I don't know how to use colors. Anyway, so you can see that these are big spots. These should be the marked vertices. And then maybe for simplicity, you start with some single vertex S. So then the commute time, which is from the distribution sigma that you have to the marked vertex M, will be the effective resistance from sigma to M times P, which is the total weight. The total weight of the graph edges. So this effective resistance, so how is it defined? Well, you have a distribution sigma, and you will want to start a flow. Like, think about sigma as a current source. So it will want to induce a unit flow in your graph, and and this unit flow will flow on some edges. Some current goes here and here and here, and it needs to reach the marked vertices, which you can think of as sinks. And this effective resistance is really just if you want to drive a unit current through this network from the distribution sigma to the marked set M, then what is the power dissipation in this network, where the weights, so like the weight should be like the conductance of the edge, which is like 1 over the resistance. So there's some nice mathematics here, and also some connection to high school physics. But so this is how you should think about the weight, as like how easy it's to conduct current along that edge, which is just 1 over the resistance. And then in this network, you can just like figure out what is the resistance of this network, and then that will be, and you multiply to the total weight, and this is this is called the commute time, but in this electric network framework. And when you have when sigma, this distribution is indeed like a single vertex, then it's indeed a quantity like commute time, so expected time from going from S to the set M and then going back to S. So in some cases, it is really like a combinatorial quantity. If you have a distribution and then it's more complicated, then it's not so clear how to interpret it in a combinatorial picture, but this electric network definition always works. And so the result here is of Belows that you can find quadratically quicker than this. So you can find marked vertex in time, which is you need to set up the initial distribution sigma and then plus square root of this commute time times update plus check. So Belows in his original work only showed, again, as analogous to the Szegedy framework, only showed how to detect the presence of a marked vertex in this time. And now we were able to prove it actually maybe up to some like square root of log factor. You can also find a marked vertex in this time. And this is actually a strict generalization of the previous result, because if you take sigma, if sigma is just the stationary distribution, then this C sigma M is just the heating time. So it really is a strict generalization of the previous result. And but it's much more general. And for example, you can apply it to backtracking. So in backtracking, you have some binary graph where you search, and it's like a set solver or something. And then at every vertex, which is like an assignment, like a partial assignment to your variables, you can see if you already see a contradiction, and then you just retract, you go back. Or if you don't see a contradiction, then according to your heuristics, you just choose to assign a new variable and then continue. And this is like a breadth first search for solving constraint satisfaction problems. And but difficulty is that kind of the graph is unknown. The structure of the graph is unknown. It's very different from the Johnson graph case. But once you are at the vertex, you can always decide what to do. So you can locally do the walk that you need, but you don't have a global understanding of the structure. And so one can see that if you have a binary tree of like depth n, so here where you will start, the starting vertex will be just at the root in this case, and maybe you have some paths which are just like cut off because they are not good. These are like not there, but then there are some marked vertices which are already good. And now you want to find them. And so in this case, if the depth is, let's say, I don't know, D is the depth of your graph, then you always have a path from S to a marked vertex, which is at most D. So this effective resistance of sigma to M is always less than or equal D. because I just assign unit cost to every vertex, then the resistances along the path is just add up. So the effective resistance is at most D, and the total weight is just approximately like the size of this backtracking tree, size of the tree, and which I just denote by T absolute value, and therefore the complexity, this C sigma m, is at most T times D. And if, like in typical scenarios, the depth is much smaller than the actual size of the tree because it's a binary tree or like something like that. Therefore, this is just a log factor. And then this algorithm actually gives you a quadratic improvement compared to the tree size. And now we have the general results, so you don't need to worry. Like previously, Ashley Montanaro had this nice application to backtracking of this law framework. So this is due to him. And he needed to do some extra work to actually find the mark vertices because it was not generally available at that point, but now you can just apply the general theorems. And you can see that you can get basically quadratic improvement for backtracking. And later there were some other improvements on this by Andy Sambainis, who also devised an algorithm for estimating the tree size. So here a problem could be that if you have some heuristics which tells that, okay, first try assign this variable 1 and go left. And then if you have some ordering on the vertices, then maybe your classical heuristics actually finds a marked vertex much quicker than the entire size of this tree. And then maybe this quantum algorithm, which kind of has a quadratic improvement in terms of the entire tree, is much worse than the classical algorithm, which also has some good intuition where to look first. But Andy Sambainis and I think one of his students, so they devised an algorithm which also could somehow estimate the size of the search tree and just do an exponential search on the tree size and basically prune the tree for a given size and then get the quadratic improvement there. And because it doesn't look first, it only looks at a small fraction of the tree, it basically gets a quadratic improvement in terms of the actual classical runtime. So if you have a good heuristics, then it even gives a quadratic speed up over that, not just the entire tree. It's a slightly more sophisticated techniques. And well, I'm sure and I hope that there are also more applications of this quantum walk framework to other graphs, other problems. But yeah, I think I will stop here. So these are the two main tips that I wanted to tell you. The first is the classical Szegedy-Ambainis framework for in the case when you have a stationary distribution, and this is the more advanced version, which is maybe this commute time is slightly less intuitive, but it's more general result telling you how to find a marked vertex from arbitrary distributions in arbitrary weighted undirected graph. So if you have any questions, then please.
Thanks, Andras. Yeah.
Thanks, Andras.
Thank you.
Overview.
So, Venkata, did you have a question?
No, I don't have a question.
So I had a more general question about, so going back to, you said that you can, the t-square improvement in time. I guess, maybe you said this and I missed it, but what is intuitively the reason for this quantum improvement? So I registered that you have this improvement in the quantum setting, but where does it come from?
Where does it come from? Okay, so I have several answers to this. and maybe I try this one. So here is this like quantum walk operator, and this has this funny structure. And what it happens, it's like unitary operator which uses this original walk. Somehow what ends up happening is that in some sense, the eigenvalues of this P matrix, these are converted to some phases which will start rotating. And somehow, so imagine that you have here some, okay, so first of all, the largest eigenvalue of P will be always 1, and that corresponds to the station distribution. And the second largest eigenvalue, that is this delta, is basically this eigenvalue gap. So like this lambda 2, lambda 1 is 1 always. Mm-hmm. Lambda 2 is like 1 minus delta. And somehow these eigenvalues will be somehow moved to a vector. So this will be some corresponding, like psi 2 will be a vector corresponding to this eigenvalue. And then the cosine of this will be just this, like 1 minus delta will be the cosine of this. But then the angle between these two vectors, that's basically like approximately square root of delta. And then what ends up happening that these vectors will just start rotating with this angle that they have. And since the angle is quadratically larger than the gap, than the original eigenvalue, these rotate like quadratically faster. And what happens when you mix, basically, if you just repeat your Markov chain many times, then all the other eigenvalues get killed and only this one remains. So this is mixing. Mixing means that basically all the other disturbances in my state goes away and I just converge to the stationary distribution. And the time of this is mixing time, which is basically 1 over delta. But this mixing somehow happens quadratically faster in the quantum case because these things rotate like quadratically faster.
Okay.
And you know, these like rotations and then like all this stuff which I just described now is like really like, I don't know, maybe confusing, maybe in a high level, but then rotations and like those things, these are just exactly like Chebyshev polynomials. So this Chebyshev polynomial of the Markov chain matrix P that just basically tells the same story but in a matrix function language.
Okay.
And if I turn to the matrix function language, I can tell you that so if I take P to the T, which is T step of the walk, that can be approximately decomposed as like sum from some like minus square root T to square root T, some Chebyshev of polynomial K of P, and some coefficients, I don't know, some QK. So polynomial x to the t can be decomposed as a Chebyshev polynomial of like square root t degree. And it gives a super good approximation of that. And if I just plug in a matrix to this polynomial, then I get the matrix polynomial approximation. So, and that's how I get this like tilde operator. Somehow I approximate t steps of the quantum of the actual classical walk by somehow square root t Chebyshev polynomials of up to degree square root t, and I just average them over, and then I get a very good approximation of t steps of the classical walk, and that's how it happens. And again, like why it's possible, the intuition behind is this like quadratically larger angles here. Yeah, and these Q coefficients, these are also actually, this is the probability distribution. So it is a super nice approximation. I can just basically randomly sample the K with probability QK and then do this quantum walk operator, which does give me this Chebyshev polynomial. That would be good enough. So this approximation is like a linear, like a a convex combination of Chebyshev polynomials give a super good approximation of a quadratically larger monomial that if I just plug in a matrix there, this transition matrix, it just gives me a very fast quantum algorithm, quadratically faster.
Makes sense. Okay.
But you know, actually, like the first version I explained, that's how people understood these things before. And the second, the matrix function picture that I explained, that's only like 1 year old or 2 year old understanding. This is called like fast forwarding of Markov chains.
Okay, that's a cool name.
Yeah, and this is a technique by Apers and Sarlat. And this is also, I think, yeah, this paper is from 2018, but the implications were understood a bit later. Like, I mean, some implications were, of course, there already, but the unfolding of the big story happened last year. And basically, this fast forwarding is the reason behind that all these algorithms that previously could only like detect elements because somehow these crazy rotations can be detected, but unclear how to use them. Now we also know how to use them to find a marked element.
Okay, makes sense.
So in a way, actually, these quantum walk speedups can be thought of as a generalization of the Grover speedup. There also very similar thing happens. This probability is like, the success probability has also this relation to the angle of rotation there, and that's how you get the quadratic advantage. The main difference is that in Grover search, you only have basically one angle and like one rotating thing, whereas here you have like several eigenvalues and more rotating things, so it's like more complicated and more general to analyze. But somehow the very basic intuition is just it's like the same. You can clearly do it as a generalization of Grover search. Okay, so I hope that it was accessible enough. I wasn't exactly sure like what level to aim at, but I tried to make, you know, kind of also give a hint, balance like how much hint I can give on like the details or like the underlying things under the hood, while not forgetting that you ultimately probably want to apply these results to some nice problem and break some crypto schemes. So maybe you more care about the applicability than just the final results.
No, thanks. I think this was a really nice overview in terms of covering the possible applications and where the and specifically in terms of applicability for us. So I really enjoyed it. I'll stop recording.